Good evening to those in my time zone, and welcome to everyone else. My name is Joachim Holmberg, and I'm going to present a webcast on cross-country skiing biomechanics using measurement-driven full-body simulation. And myself, I'm a PhD student, mainly working in Östersund, Sweden, and my background is within mechanical engineering. I will present my work in skiing biomechanics carried out at Sweden University in Östersund. And as usual, Søren Törholm and Arne Thies of Antibody Technology are also with us tonight. And here you can see a short explanation of the questions and answers panel. And of course, you're welcome to ask as many questions as possible during the event. The outline for the presentation is cross-country skiing, a short introduction of the subject, two examples of use for musculoskeletal cross-country skiing biomechanics, and also an in-depth view of my latest simulation model for double cooling, including how to drive a 3D body model from 2D motion data. Also some comments on static optimization for fast full body motion, and in the end a couple of conclusions. So a short introduction. Cross-country skiing comes natural in Östersund, Sweden. We have skiable snow half the year, and there is a great deal of local interest. For example, last week we hosted the World Championships in biathlon, which is basically skiing with a rifle on your back. Traditional skiing biomechanics is just experimental testing, and simulations should add further insight to the subject. And for those of you who are familiar with the antibody modeling system, you know that there are two main choices. First, what kind of body model to use, develop your own, or take one from the repository and then adapt it for your needs. The second choice is motion and external forces. Conduct experiments to gather the motion and forces, or to make an educated guess and use that. For me and my co-workers, the choice has been to carry out our own experiments to gather the motion and external forces, then to use a body model from the repository and modify it as needed. In this way, we can focus on the application and the simulation models, in this case for cross-country skiing. And the main goal of my work has been to explore the possibilities for computational musculoskeletal biomechanics in cross-country skiing. So, after the short introduction, some examples of use for cross-country skiing biomechanics. Finding antagonist muscle pairs. This is an interesting application that you might not think of at first when talking about skiing biomechanics. Some skiers are believed to have a muscular imbalance around the shoulder complex due to very strong chest muscles. The problem is sometimes referred to as rounded shoulders. In sports gear skate techniques, the range of motion for the upper arm is large, usually more than 180 degrees. If the chest muscle is too strong compared to the antagonist, the passive resistance of the chest muscle may hinder the backswing, and that also may lead to that the technique is not as good as it could be. And the antibody modeling has a solution for this. And the theory is that by changing the passive resistance of the muscle in the body model, the antagonists have to work more, while the other muscles should not be affected. Thus, we can find the antagonist by using such a simulation, and hopefully the imbalance can then be fixed by training the antagonist, and the motion in 4K escape should probably become better. And the antagonists that were found to pectoralis major for the fourth gear escape technique was the rhomboid. I hope you can see the marker here from my mouth. Rhomboids are located here. Trapezius, big muscle, and it's the scapular part that are the antagonists. Intraspinatus, the marking is here, yes, and this muscle, and then the extending part of the latissimus dorsi, this muscle here. Another example of use for this technique is what if question. And one example here is load distribution between muscles. Studies and literature show that faster skiers have a different skiing style or movement pattern than slower skiers. It's not only the pole passes or pulling frequency that are different, but also the style of the movement pattern. And the question is, does the load distribution between the muscles, in this case teres major and latissimus dorsi, change depending on study found in literature? Measurements of joint angles and EMG, muscle activity, indicate that the load distribution indeed change between teres major and latissimus dorsi when arm abduction and elbow angle changes. And faster skiers commonly use greater arm abduction and smaller elbow angle as toe plant, which is considered to be a more modern and a so-called wide elbow style. Also, it's speculated that the faster skiers utilize the triceps. And the simulation results show the same tendency. With greater arm abduction and smaller elbow angle at toe plant, teres major carried more of the load. And this is left side, left upper arm, left shoulder seen from behind. And we have teres major here, and latissimus comes up here from below. So it's the load distribution between those two muscles. And preliminary simulations also show a clear difference in triceps behavior. The lateral and medial parts of the triceps require much less activation for this modern style wide elbow. So it's very interesting application, and I think an interesting example of use for this technique, cross-country skiing biomechanics using simulation. Can we take a short break so that those without sound have get some time to fix that? For those of you who didn't hear me before, I hope you do it now, because now we're moving on and start talking about simulation models. Some basic information basic information of the simulation model. And just before we move further on, for an animation of this simulation model, please check the link here, and hopefully Søren or Arne will copy and paste this link in the chat window, so you yourself can copy and paste it into your favorite web browser and download the animation. Then you get better understanding of when I talk about the simulation model and the results. I think it's worth to point out that this simulation model is driven. That is, I use experimental full body motion data as input to the simulation. It's based on Anybody 3.0, so far in the latest version of the software, and the model repository 6.1. 464 muscles, 64 rigid bodies, and simulation model. What I mean by that is the body model and the boundary conditions. And I like the current simulation model, which I define as the body model plus the boundary conditions. In this way, I specify that a certain body model moves in a certain way while under a certain external load. And I will move on to the boundary conditions and explain what I mean by boundary conditions. To repeat, I like the context of in the context of musculoskeletal simulations, I define the term boundary conditions as the motion and external forces applied to a body model, thereby creating a simulation model. The boundary conditions are then usually applied in the software by drivers. So the boundary conditions are the motion and external forces. And in my case, I use experiments together. And in this double pooling simulation model, the boundary conditions originate from an experiment carried out using a so-called double pooling ergometer equipped with load cells at the pulpit. This ergometer works in the same way as most rowing ergometers commonly found in your local gym. The pole forces were recorded by load cells at the pulpit with a sampling frequency of 100 Hz, and motion was captured by a common digital camcorder. Spine curvature, pole inclination, and joint angles were extracted corresponding to a sampling frequency of about 10 Hz. To continue with the boundary condition, I got smooth but high forces, but at the same time as a non-smooth motion. And the problem with this is that the boundary conditions doesn't fit together, and the non-smooth motion also may get high acceleration. And the measured motion data is not just there to support the pole force curve. I will show the curve in a moment and explain that a bit better. Also, the jerk or rough motion data yields very high accelerations, as I said, which of course in turn yield very high forces. The solution in this case was to use a Bezier interpolation spline on all the boundary conditions. Before I used to use the B-spline interpolation instead, but especially my motion data seemed to be so rough, so to speak, and the muscle activation results were infested with spikes, which is partly due to the high acceleration. And the results using the Bezier interpolation spline is that motion and forces are of course altered, but the simulation model works. And the conclusion is but there is a loss of accuracy, and it's possible you should use the same measuring frequency. But loss of accuracy, the importance of the loss of accuracy is unknown at present. But it's quite clear that there's no point of measuring one data set higher by a factor of 10, as I did here. You only end up with a mismatch of the boundary conditions that may corrupt stability. Here we have some kinematics and pole force curve. And to the left we have the smooth pole force and joint angle curve after applying the Dessler interpolation spline. This was used in the simulation model, to the left here. And to the right we have the raw measured pole force and joint angles. As you can see, the motion of the joint is non-smooth. Jerky. And also it's a factor of 10 mismatch in the sample frequency, as I said earlier. And with pole force I had a sampling frequency of 100 Hz, and on the motion data about corresponding to 10 Hz. The two pole force peaks, as you can see on the top right here, just don't have enough corresponding motion data. There's a small twitch in the elbow angle curve here, but not enough, as you see. Also for the small peak here, about 0.9 seconds in the pole force curve, there is no motion difference to support that peak. And therefore, I had to use the Dessler interpolation spline. And if we go over to the left here, we have a much more smooth curve where apparently the motion now fits the pole force curve much better. And there is some loss of accuracy, of course, but on the other hand, the boundary conditions now fit together and the simulation model works. As a reminder, it's okay to ask questions. Here you can see again a short explanation of the questions and answers panel. Let's move on. Simulation model, drivers, 2D motion and 2D data, and a 3D body model. How to do? Well, create a 2D dummy without inertia properties, but with limb length matching the subject, the 2D version of the subject. Then apply motion to the two-dimensional dummy, and then let the 2D dummy guide the 3D body model. The two-dimensional dummy is, if I have a marking, in the spherical plane here, you have the 2D dummy, red and green and blue, and then you have the 3D body model around it. And I let the 2D dummy guide the 3D body model. Double pooling is essentially two-dimensional, and the 2D dummy only moves in the sagittal plane. And the body model is then constrained to follow the 2D dummy in a parasagittal plane at certain joint centers. And for those of you who know animal, I use the function any2 EQ The lower body, in this case, is a closed chain, and the marker save the constrained dot to the upper body. One problem is not to over-constrain the lower body and not to under-constrain the upper body. And my knowledge on how exactly to let this 2D dummy guide the 3D model is partly based on experience. And I have to admit that it's taking me a while to get the simulation model to work correctly. It's very easy to end up with an unstable model infested with acceleration spikes several joints. Apart from the 2D dummy, the final 3D body model is driven directly from the measurement. The body model. Well, I use the simple muscle model. That's in order to keep it simple. I use a full body model. You can ask why legs. Well, cross-country skiing is a full body movement, even double pulling. Recent studies in literature show that leg work is very important in all cross-country skiing, also even in double pulling that traditionally can be considered to be mostly upper body work. And also, even though the legs do not move that much in my motion data, they still have to do a considerable amount of work to counteract the high forces involved in double pulling. And for those of you who haven't done it yet, please see the animation, for example. And I asked Søren or Arne to give the link in the chat window so it's easy for you to cut and paste it into the web browser to download. Results. Well, the simulation model is now reasonably stable and can handle realistic loads, at least for this skiing application. And as I mentioned, it used to be very unstable, and it also earlier could not handle the loads to a full extent. And one reason, apart from the way I find the drivers and the 2D dummies, would probably be due to the new version of the software and the repository that made it easier to get a working simulation model. Muscle activation. If I compare that with studies found in literature, the activation schemes agrees fairly well if you consider that motions and pole force are usually slightly different from the studies found in literature. And we will go into some slides to compare my simulation results from the double pulling ergometry and some roller ski studies. Here we have some pictures. To the left we have again the pole force used in simulation and the motion data in the simulation. That is kinematics and pole force from the simulations of the double pulling ergometry. And also we have the kinematics and pole force from a roller ski study found in literature. And we have to compare the kinematics and the pole force before we compare the muscle activation. And by the way, there's no relation whatsoever between the authors in the two studies. It's coincidence. The names. If we look at the simulation and ergometry study, we have a total cycle time of 1.4 seconds. That is the time for one pulling cycle. And in the roller ski study, it doesn't show here, but it's 1.1 seconds. And then the pulling phase is 50% in the simulation from the ergometer study, while it's 30% from the roller ski study. And the time to peak pole force is the relative time to peak pole force is 50% in the ergometer simulation study. That is the time from pole plant until we have the peak pole force. And in the roller ski study, it's 30%. So it's a very short time from pole plant until you attain maximum pole force. The thing to remember here is one major difference between these two studies is for the ergometer, double pulling ergometer. You have to push a mass back and forth. And as you can see here, you have negative pole force, and that is due to the fact you have to not only to push the poles backwards, you also have to pull them forward. And considering the pole force curve difference, joint angles show similar patterns. And for example, we can look at the hip, and we have the hip angle for the roller ski studies, and the angle minima down here is almost exactly at where we have the peak pole force. And if we go over to the ergometer simulation study, we have the same. We have the angle minima for the hip about here, and that's almost, a bit hard to see here, but almost at the maximum pole force. And then we can look at the elbow, which has an angle maxima at the end of the pulling phase, which is about here on the roller ski study, and on the ergometer simulation study, it's about here. And we could say that it's essentially the same movement, if you consider the pole force differences. Now, if we go ahead and look at the muscle activation, compare the muscle activation, generally we have the largest total activation around peak pole force in both the ergometer simulation study, my study, and the roller ski study from the literature. And as you can see here, the black parts are with high muscle activation, and we have the pulling phase here for the roller ski study. And as you remember, the peak pole force was in the first half of the pulling phase, and most muscles are activated the most at the pole force maximum. And this is also the case for the ergometer simulation study. And here we have the peak pole force, and in line with that we have maximum activation of most muscles. Many muscles are activated slightly earlier in the roller ski study, but you have to remember that the peak pole force was also earlier in the roller ski study. The ergometer simulation study show more activation in the recovery phase, which is this area here to the right, but that's because the poles need more applied force to be transported forward, because you have the mass of the small slide wagon on the ergometer, double pulling ergometer, that you have to pull forward every time. and if you go on roller skis, the effort for the fall forward is almost nothing, just the weight of the pole. Also a general remark, muscles around the shoulder match better and muscles around at the hip and the lower trunk match worse. We will look in detail in a couple of muscles there. If we start with the triceps on the ergometric simulation study, you can see the activation is around the peak pole force, and it's rather highly activated during the whole of the pulling phase, which is also here we have the triceps for the roller ski study. Then we have the teres major, and for the ergometric simulation study, we have highest activation around the peak pole force again, and this is also the case for the roller ski study. Let's move on to another muscle, persistent dorsi, also around peak pole force, and actually largely activated during the whole movement, but a lot during the whole pulling phase, and also after the pulling phase. And this is also the case for the roller ski study, where I have some other medium activation after the pulling phase. So that is the dorsi. An example of a muscle who doesn't agree well, we have the lexus abdominis somewhat. In the ergometric simulation study, have some activation around during the pulling phase, but actually low activation at peak pole force, and while for the roller ski study it's higher during the peak pole force, so doesn't agree every time. The biceps femoris long head, as we have in the simulation study here, is an example of the leg muscle that agrees somewhat anyway to the roller ski study. And you can say that in parts where kinematics is more accurate, the activities show more consistency. So let's move on to a slightly different subject, static optimization for fast full body motion. We don't have any activation dynamics when we use any body. And without activation dynamics, the muscle can deliver full momentary strength instantly. That's because in static optimization, each time step is calculated independent of the other, which it currently means that it's hard to implement activation dynamics. Therefore, when using static optimization, it's common to restrict the method to slow and skilled motion. But then you can ask yourself, what's a slow and skilled motion? Well, gait is a commonly used example of this. But I haven't found any standards at all or conclusions for determining what to consider as a slow enough motion suitable for static optimization. And as I think I've shown, cross-country skiing is a rather fast and powerful full body motion, but it seems to work anyway with static optimization. You have the signal speed. Brain or the central nervous system tells the muscle to do something, then it takes some time for the muscle to actually contract. And even methods that claim to include the activation dynamics usually don't include the first step. steps from when the brain tells the muscle to do something. I'm not sure if that is any importance, but it might be. Also, there are probably more steps than the one shown above. Then another important factor here is what is good agreement? Is it agreement with reality, or is it agreement with EMG? EMG is the method where you still don't really know the relationship between the measured electric potential and the muscle force. But then we can also ask ourselves, does it really matter if you add one more piece of inaccuracy? The results are not true with activation dynamics and falls without. It's only in shades of gray. It depends on your goals and the purpose of your simulation. Static optimization might be good enough. So, let's end with some conclusions. Cross-country skiing, but biomechanics using musculoskeletal simulations can add knowledge that would be hard to achieve with traditional experimental methods alone. And in addition to the two examples shown in the presentation, how do you isolate just one variable on a living subject racing at full speed that can be almost 30 kilometers per hour? Or how do you find muscle activation of deep laying muscles like ellipsoa, which is a muscle that's considered important for skiing? 2D motion and 2D data can drive a 3D body model by using the trick of a two-dimensional dummy. And especially in this case where we have a motion like double pulling that essentially is two-dimensional, this trick works fine. But I have to admit that I intend to use a 3D mocap system like the Python to do a complementary study on double pulling biomechanics. And also, fast full body motions like cross-country skiing does not seem to be too fast for the method of inverse dynamics and static optimization. But to be sure about this, or as sure as you possibly can be in this line of work, a thorough validation study together with some clever thoughts of what's fast has to be carried out. But to sum up, much more work is needed on this subject, at least in my opinion. And we have some key references to the presentation. Reference 1 and 4 are deals with inverse dynamics, static optimization, the object function, and so forth. Reference 2 and 3 mostly deals with biomechanics of cross-country skiing. And just to add, most of the work here was carried out at the Department of Engineering, Physics and Mathematics at Mid-Sweden University in Östersund, Sweden, and all experimental work was carried out at the Swedish Winter Sports Research Center, also at Mid-Sweden University in Östersund. But I'm also affiliated with the Division of Mechanics at Linköping University in southern Sweden. And thank you all for listening, and welcome back to other webcasts from